Hello and good evening. Today we'll be presenting to you our presentation for assembly. I am Murali Garachi and I have Ryan as my partner. So let's get started. Before we start, let's just take a look at how Hello World would look like if it was written in assembly. We're going to be discussing all the elements in this code, and hopefully by the end of the presentation you may have a gist of what this is doing. This is our agenda. We're going to go through the description of what assembly is, advantages, disadvantages, structure, basic syntax, general registers, and factoids for you. So in a nutshell, assembly is a low-level programming language, and language in quotes because for some people this is a category of programming language, not a language itself. Lower level because we are talking about a language, quotes, that is close to machine code. It was invented in 1947 by Kathleen Booth, and up to the introduction of Fortran, it was the norm for writing code. So whatever you needed to write code in for any computer, you would be writing in assembly. For the advantages, we have performance optimization because it's a low-level language, it's closer to the hardware, you can maximize efficiency. It's a low-level access because it is a low-level language. You have access to particular features from hardware that you wouldn't normally have were using a high-level language. And porting interfacing, and that is because if you understand how assembly works and you can actually write code in assembly, it is easier for you to quote port code from different machines from one to another. It's just easier, not that it's easy, okay? For the advantages, the first one is steep learning curve. It's not an easy thing to learn. Lack of portability because although, yes, you could, quote, port things around, it's not that you can port, you have to rewrite everything from scratch. So when we say port, in the advantages, we just mean like if you know how to write in assembly, it may be easier for you to write the same code again, but for another machine. And it's hard to debug just because you have tons of lines to go through, and it's not as abstract as it is for high-level languages, so it's much more harder to grasp. For the assembly structure, we have three main sections: text, PSS, and data. Text is the main code, whatever you want to accomplish with assembly. PSS stands for block starting symbol, and it will hold all the variables, whatever is mutable in your code, and the data will hold whatever is immutable in your code. Important to say that for the text section, you must have a declaration called global_start because that statement will tell you where your program actually begins. For the basic syntax, we have four components: label, mnemonic, register, and operand. The label is optional and it's just in a specific memory location or logical markers. If we were to compare this to a high-level language, it would be something like the function name. The mnemonic is just a CPU-specific instruction. The register is optional. It is, again, just a small fast storage location within the CPU where you're going to store or retrieve information from, data, sorry. And the operand is also optional, and it's just one port, whatever the mnemonic needs, if you need something. So if you're using add, it will probably require an operand there, which is the data or address that you're gonna need to, you wanna change or add or remove, whatever. For mnemonic examples, we have four groups there in the slide for you: data movement, arithmetic, logic, control flow, and system. For control flow itself, it's interesting to see, for instance, the JE, which means jump if equals. It's just a sort of if statement that will help you jump around your code. And we're gonna go through this once we are getting into our demo for you. And here you have an example of a statement just saying that the value 10 is to be moved or stored in the register EAX. For general registers, we have data registers, pointer registers, and index. Data registers will hold and manipulate data during a program execution. The pointer registers just hold a memory address of a specific location in the computer's memory. And the index just facilitates efficient access to elements in arrays or data structures in memory. We have four 32-bit data registers that are used for arithmetic or logical operations. And you see A is for accumulator, B for base, C for counter, D for data. And for the 32, you may have 8-bit or 16-bit sections that you may use. So AL, for instance, is a 8-bit section from the 32-bit register EAX. We have three 32-bit pointers registers that are used for efficient memory access. So we have instruction pointer, stack pointer, and base pointer. For index registers, we have two 32-bit registers, one for the source index and one for the destination index, and both are used for string operations. And here are some factoids for you related to gaming. So Mortal Kombat was allegedly written in assembly for its arcade version. Sega Saturn used assembly to improve its performance. And Doom actually used assembly for the rendering portion of it. And apparently it was a common thing to use assembly for specific portions of programs to speed them up. Here are references, and let's jump into the program demo. All right, so our program will convert a string that will be given by the user to uppercase. We have our three sections of our code here. The section text will be discussed in the next slide. For now, we're going to be discussing data and BSS, remembering that BSS stands for block starting symbol. For data, we will hold all the variables that are not changed. So in this case, we are initializing and declaring the variable output. DB stands for defined byte, and then uppercase string, whatever is in this single quote, is the value that we want to store. And the 0 here just means that we're telling the computer this is where the string ends. For the section BSS, we'll have all the variables that will change during the execution of our code. We have input and output buffer. The input will be whatever the user will give to us, and the output will be the conversion of whatever was given into uppercase. Res stands for reserved byte, and we're using this instead of defined byte because we don't know what input will look like yet because we did not get the input from the user. So this is just reserving bytes, and we are reserving 100 bytes. Each character is a byte, so we are reserving a string that is up to 100 characters long. Same goes for output buffer. Let's take a look at our section text. In the section text, we are going to start with the declaration global start, just because we need to do that. And then we have the label start here, which will have the instructions that we're going to run. The first set of instructions here will set the stage to grab the input from the user. So for the first line, we are moving 3 to the EAX register. EAX, if you don't remember, is the register for the accumulator. And for this particular register, when we're moving the value 3, we're telling the computer, hey, we are going to read something. Then for the move EBX0, this is telling the computer from where you're going to read something. So in this case, 0 for this register means that we are going to be using the standard input, which is the keyboard. So we're telling the computer, hey, we're going to read, and we're going to read from the keyboard. The third line will just tell the computer that input will be stored in the ECX. And if you don't remember, ECX is the counter register. And then for the fourth line, we're just telling the computer that the data that we'll be holding is 100 bytes. Then you have this int OX80. This is a system call. Int stands for interrupt. This is a system mnemonic. And what this is doing is telling the kernel to do its thing, which in this case will be read the keyboard. For lines 6 and 7, we'll still be setting the stage for the string conversion. This first line, if you don't remember, that's for the register that holds the source index. And in this case, we are pointing that to input. And for the destination index, we are referring that to the output buffer, which is the string that will hold the uppercase string. And then we will move to the convert loop, and this is where the action will take place. The first line here is telling the computer the following. We are retrieving 1 byte, which in this case will be one character from this address, which is the input address. and we're gonna store it in the L register, which is the accumulator register. Remember, that's the 8-bit one that we have. Then we are going to compare this now byte that we just retrieved with 0. And then we are going to see if that's equals 0, and this means jump if equals. If L is equals 0, then we're going to run the convert done, which is this guy here, but we're not going to touch this right now. So these 3 lines are basically just checking if the current character that we're looking at is null. That not being null, we go to the second comparison, and this one we're comparing the current byte that we moved here with A. And then we go to jump if lesser. So for the ASCII table, the uppercase letters come before the lowercase letters, and the distance between them is 32. So if A uppercase was 0, then A lowercase would be 32, the code, the ASCII code. So we're just comparing to see if the value in the register AL is lesser than the lowercase a, then we're going to go to a skip conversion because we are assuming that the character is uppercase already. And then to skip conversion, we go to this label here, but we're not going to check this right now. If the character that we're looking at right now is not uppercase, then we're going to take a look and see if AL is greater than Z, and that's what we're doing here. If this is greater than Z, then we're going to skip conversion as well. And that is because whatever is after lowercase z, it's probably a special character, not a letter itself, and therefore it wouldn't need a conversion. So if the character is not null, if it's not an uppercase letter already, and if it's not a special character, then we're going to convert this character to the uppercase. So we are subtracting 32 because the distance between the uppercase and lowercase letters is 32. So we are deducting 32 from the current value, and that will take us to the uppercase character of that lowercase character we're looking at. After converting the current character to uppercase, we are going to enter into the skip conversion label, and that is because we are following instruction by instruction, right? So what this first line will do is it will get the current value of AL, and then it will store that byte into the EDI. Then we are going to increment ESI by 1, which will basically just move one character. And we're going to do the same for the source and destination. So we're going to move one character from the input and then one character from the output buffer, which is our converted string. And then we're going to jump to convert loop again. And we're going to do this character by character until we get to the end of the string, which will then jump us to the convert done. And here, what this very first line will do is it will tell the computer that we reached the end of the output buffer, which is located in the EDI. And remembering, if you have brackets here, it means that we're looking at the address of this register, and we are basically just telling the computer, hey, we finalized converting the string, so let's just end the string right now. Then the following 5 lines of code here will display the output variable, which in this case is just that message telling uppercase string column space that we initialized in the data section. So whenever we are moving forward to the register EAX, it's telling the computer, hey, we're going to write something. And whenever we are moving 1 to the EBX, which is the base register, we are telling the computer, hey, we're going to print something on the screen. Then for the move ECX, we are just telling the computer, hey, this is the value that we want to output. And for EDX, we are just telling the computer, and the length of this output is 18 bytes, which in this case will be 18 characters. And then we are again interrupting the software, let me say it that way, which is just we're making a system call and asking the kernel to do its thing, which in this case will be print the output. And the output is uppercase string space column space. Then we are going to do the same thing, but in this case, instead of printing the upper string message, we're actually going to print the result, the output that we want, the converted string. And again, we are just telling the computer, hey, we're going to write something, and we're going to write something to the screen, and then this is the variable that we're going to write, and this is the length of the variable. And then we're telling the kernel, hey, do it your thing. Last but not least, we are then moving the value 1 to EAX, which is just telling the computer, hey, we're exiting this operation. Then we are going to perform an XOR into the EBX register, and this is just clearing the register, which will return the result 0, and that's what we want. And then we are just calling the system again to perform the exit, which is the instruction that was provided in this line here, the first line of this block. And we're done.